Welcome to Methods in Biostatistics. Today, we are diving into one of the most powerful tools in science, hypothesis testing. If you have ever wondered how researchers prove that a new medicine actually works, or how we know a specific diet is truly effective, this is the mathematical engine behind those discoveries. We are going to build your understanding from the ground up, step by step. By the end of this video, you will know exactly how to put a scientific claim on trial and uncover the truth hidden inside the data. Let us get started. To understand how hypothesis testing works, imagine you are sitting on a jury in a criminal court trial. The fundamental rule of the courtroom is that the defendant is considered innocent until proven guilty beyond a reasonable doubt. As a juror, you do not assume guilt right away. Instead, you carefully look at the evidence presented. If the evidence is incredibly strong and makes the assumption of innocence look completely ridiculous, you reject the idea that they are innocent. If the evidence is weak, you simply say there is not enough proof. Hypothesis testing works exactly the same way, but we are putting a scientific claim on trial instead of a person. Now that we have our courtroom analogy, let us look at the formal definition. In biostatistics, hypothesis testing is a step-by-step mathematical procedure used to make decisions about an entire population based on a small sample of data. Whenever a researcher conducts an experiment, they are trying to see if a specific treatment, condition, or relationship actually exists. The biggest question is always this: did the treatment actually work, or did the results just happen by random chance? By calculating the probability of getting our sample data under a baseline assumption, we can make a mathematically sound decision to either reject or keep the status quo. You might be wondering why we need such a strict mathematical process. Without hypothesis testing, modern medicine and biology would be completely based on guesswork. Imagine a pharmaceutical company tests a new headache pill on 10 people, and 7 feel better. Without statistical testing, they might rush to sell it as a miracle cure. However, hypothesis testing forces us to ask a critical question. Could those 7 people have gotten better just by random chance, even if the pill was completely useless? Regulatory agencies like the FDA use this exact process to protect patients from ineffective treatments, ensuring that every medical claim is backed by solid, undeniable evidence. To translate our scientific question into math, we define 2 mutually exclusive statements. This is where our formula comes in. The symbol H0 represents the null hypothesis. This is our baseline assumption of no effect, which always contains an equality sign. It means nothing is changed. The symbol HA represents the alternative hypothesis, which is the new claim the researcher is actually trying to prove. In this equation, the Greek letter mu represents the true average of the population we are studying, while mu0 represents the known historical baseline value. If the difference between our sample mean and this baseline increases, our evidence against the null hypothesis becomes much stronger. Now that we have set up our hypotheses, we need a way to measure how strong our evidence is against the null hypothesis. We do this by calculating a probability called the p-value. The p-value is the probability of observing our data, assuming that the null hypothesis is completely true. Before the experiment even begins, we set a strict threshold called the level of significance. We will compare our calculated p-value against this threshold. This crucial comparison ultimately dictates whether our scientific claim survives the trial or fails. Let us look at the mathematical rule for this decision. This brings us to the ultimate decision rule of hypothesis testing. We reject the null hypothesis if p is less than or equal to alpha. Let us break down these symbols. The letter P stands for the p-value, which tells us the chance of our results happening by pure luck. The Greek letter alpha represents the level of significance. This is the maximum probability of making a mistake that we are willing to accept, usually set at 5%. If our calculated p is less than or equal to alpha, the results are so rare that we must reject the null hypothesis. If the p-value increases and becomes larger than alpha, we fail to reject the status quo because there's too high a chance that our results were just random noise. Before we can find our p-value, we must calculate a test statistic. This formula calculates the z-score, which measures exactly how unusual our sample result is. In the numerator, we subtract the baseline mean, mu0, from our sample mean, x bar. This tells us the raw difference. In the denominator, we divide the sample standard deviation, s, by the square root of the sample size, n. This entire denominator is called the standard error, which represents how much we expect the sample mean to naturally fluctuate. By dividing our raw difference by the standard error, we find out exactly how many standard errors our sample mean is away from the baseline. Let us see this formula in action with a real example. Let us walk through a concrete example. Suppose the historical average weight loss for a standard diet is exactly 2.0 kilograms. A nutritionist tests a new diet on 36 people, finding an average weight loss of 2.5 kilograms with a standard deviation of 1.2. We want to know if this new diet is genuinely different using a 5% significance level. First, we set our null hypothesis to 2.0 and our alternative to not equal to 2.0. We calculate the standard error by dividing 1.2 by the square root of 36, giving us 0.2. Next, we find the z-score by dividing the difference of 0.5 by 0.2, which equals 2.5. Looking this up, our p-value is 0.012. Because 0.012 is strictly less than our 0.05 threshold, we reject the null hypothesis. Physically, this means the new diet is genuinely effective. Let us look at a slightly more applied example involving medicine. A standard medication lowers blood pressure by an average of 10 millimeters of mercury. A company tests a new drug on 49 patients, observing an average drop of 12 with a standard deviation of 7. They want to prove the new drug is strictly better. Because they want to prove it lowers pressure more, we use a one-tailed test. The alternative hypothesis is that the mean drop is strictly greater than 10. We calculate the standard error by dividing 7 by the square root of 49, which simplifies beautifully to 1. Our z-score is the difference of 2 divided by 1, giving us 2.0. The standard normal table tells us the p-value is 0.0228. Since this is less than 0.05, we reject the null hypothesis. The new medication is statistically significantly better at lowering blood pressure. Now that we have calculated these values, let us visualize exactly what is happening. The diagram you are looking at perfectly illustrates how we make our decision. The large bell-shaped curve represents all the possible sample results we could get if the null hypothesis were completely true. Notice that the vast majority of the area falls right in the middle, shaded in blue. This is the fail to reject zone. The red shaded tails at the far ends represent the rejection regions, which correspond to our significance level, alpha.
When our calculated test statistic lands far out in one of these red-shaded tails, like our z-scores of 2.5 and 2.0 did, it means our result is too extreme to be a mere coincidence. Hypothesis testing is simply about drawing this line in the sand and seeing which side our data falls on.
We have covered a lot of ground today, so let us summarize the most important ideas. First, hypothesis testing is the ultimate gatekeeper of scientific truth in biostatistics. It provides a rigorous, objective framework for deciding whether an observed effect is real or just a product of random chance. Second, by setting up a null hypothesis as a baseline and demanding strong mathematical evidence to reject it, we protect ourselves from making false claims. Finally, whether you're testing a new diet, a life-saving drug, or an environmental change, the mathematical steps remain exactly the same. You have now seen how to set up hypotheses, calculate a test statistic, and make a strict decision using the p-value. Mastering this process allows you to make confident, data-driven decisions that can truly change the world.